Okay, so in the last video, we talked about Fourier series, and in this video, we are going to go over some Fourier series examples. Okay, so let me just remind you that if f of t is a periodic function, okay, with period t, then the Fourier series for f looks like this. It's a big sum of these Fourier series coefficients multiplying these complex exponential signals. Okay, so that's what the Fourier series for f looks like. Okay. So it's a bunch of these complex exponential signals. And the frequencies of these complex exponential signals are all integer multiples of the fundamental frequency omega naught of f. And then we multiply these complex exponential signals by these Fourier series coefficients, the f sub n's, and we add them all up. Okay. So that is our Fourier series. And if you remember from the last video as well, there's a formula for how to find these Fourier series coefficients and integral. But actually, the first few examples we're going to do today, you don't even need that formula. Okay, we're going to find other ways to avoid having to do integration and still be able to get the Fourier series for a function. Okay, so that's what we're going to start with. And so let's look at f of t. Let's start off real simple. Let's just say, what if our function is cosine of 3t? Okay. Then what is omega naught? We need omega naught to write down the Fourier series. Well, it's easy for sinusoids, right? Cosine of 3t. We saw in a previous video that 3 right there is the fundamental frequency, omega naught. Okay. So now how can we try and write cosine of 3t as a sum of complex exponential signals, okay, multiplied by constants? Well, if you remember from the complex numbers review video, we actually have a way of writing cosine in terms of these complex exponentials. And that's to say cosine of 3t is e to the j 3t plus e to the negative j 3t over 2. Okay, so we've seen this before. And now let me just bring the 1/2 outside of both those terms. And you can see, wait a second, this looks really very much like this Fourier series up here, right? It's a sum of complex exponentials multiplied by constants. Okay. And so, yeah, it turns out that this actually is the Fourier series. This is the Fourier series for f of t. We've just taken our function and manipulated it so that it became its own Fourier series. There it is. It's right there. Okay, now let's try and make it look exactly like this sum so that we're able to read off what the Fourier series coefficient should be. And it looks pretty similar. I would say the only difference is that here we have e to the j n times omega naught, and here we don't have n times omega naught. We just have a couple numbers. So let me rewrite it slightly differently. I'm going to write it as e to the j, and now I want to write 3 as some integer n times omega naught, because remember, n is always an integer. Okay, we're summing over that variable n. So n is always an integer here in the Fourier series. Omega naught is 3. So how can I write 3 as an integer times omega naught, which is 3? Well, of course, it's just 1 times 3 times t plus 1/2 e to the j. And now I have the number negative 3. So I can write that as negative 1 times 3 times t. Okay, now this is exactly the form of the Fourier series. We have a coefficient times e to the j, an integer, times omega naught times t. And same for this term. Okay, so this is exactly in the form of the Fourier series. And so now we can read off what the Fourier series coefficient should be. Notice f sub n, the nth Fourier series coefficient, is multiplying e to the j n times omega naught. So you can see those two n's are linked up there. Okay, those two n's are linked up there. So here, n is 1, and so that means from this term, I can see f sub 1 has to be a half. Here, n is negative 1, so f sub negative 1 has to be a half. And then there's no other terms. Those are the only two terms. And so I always write that f sub n equals 0 otherwise. Okay, because we want to specify the Fourier series coefficients for all values of n, all integers n. Here I've specified it for the two non-zero values. or the two Fourier series coefficients that are non-zero, f sub 1 and f sub negative 1. And for all the others, the Fourier series coefficient is just 0. Okay, so no integration, but we found the Fourier series for cosine of 3t, and we found the Fourier series coefficients. Okay, so let's do another similar example. What happens when I have sine of 3t? Well, again, okay, omega naught is 3. It appears right there. And we can do a similar thing, right? We also have a way to write sine in terms of complex exponentials. This is e to the j 3t minus e to the negative j 3t all over 2j. This is also from that complex numbers review video. So now I'll take those coefficients outside again. And again, this is the Fourier series. We've just rewritten our function so it looks exactly like its Fourier series. So it's in the form of its Fourier series. Yeah. And now we can do a similar thing and make it look exactly like the Fourier series to get the Fourier series coefficient. So again, I want to write this 3 as an integer times omega naught. So I get 1 over 2j, e to the j 1 times 3 times t, minus 1 over 2j, e to the j negative 1 times 3 times t. And so yet again, we can see, right, the nth Fourier series coefficient is multiplying e to the j n times omega naught t. So here we can see that this one, f sub 1, must be that value, 1 over 2j. Okay. Here I see that f sub negative 1 has to be that value, negative 1 over 2j. And then again, f sub n is going to be 0 otherwise. Okay, so pretty much the same as the first example, but a little different. Now, the Fourier series coefficient values are purely imaginary. Okay, in the first one, they are purely real. Now they're purely imaginary. Okay, for sine. All right, let's keep going. So what about the function cosine squared of 3t? Okay, what happens then? Well, I think we saw a similar type of function before, one of the earlier videos, but anyway, cosine of 3t squared looks something like this. Okay, so this is cosine squared of 3t, and compare that just for reference to cosine of 3t, which looks like this. Not the best drawing. Okay, where that's one period. Okay, and we know that cosine of 3t, what's the period? Well, it's just 2 pi divided by the fundamental frequency. So it's 2 pi over 3. And you can see, comparing this to the above, that that should be that point right there. That is 2 pi over 3 and the cosine squared of 3t function. But we can see the period of cosine squared of 3t is actually half of that, right? Because look, it repeats already after this amount. Okay, cosine squared does. So that's pi over 3. Yeah, I'm just finding the period of cosine squared of 3t. And so from these drawings, you can see the period is pi over 3. And so the fundamental frequency is going to be 2 pi divided by pi over 3, which is just 6. Okay, and we need that fundamental frequency because it appears in our Fourier series, right? So you always have to make sure you get that so that you can make sure you specify the Fourier series correctly. All right, so now we actually have to find the Fourier series. How can we do it? Well, again, here we have cosine of 3t squared. We have a way to write cosine in terms of complex exponential signals. And so if we do that, maybe we can manipulate the equation we get to make it look like the Fourier series. That's what we're going to do. So this is just e to the j 3t plus e to the negative j 3t over 2 all squared. Okay, I can take the 1/2 squared out and I get 1/4. Now what happens when I square the sum? Well, I'm going to get the first term squared, which is e to the j 6t, plus 2 times the cross term. Okay, so 2 times this times that, right? Because when I square it out, I'm going to get this times itself plus this times that. plus this times that, plus this times itself. So I'm just going through those four terms. So I'm going to get 2 times this times that. The cross term is just foiling. Okay. And then plus this term squared, which is e to the negative j60. But now right here, e to the j3t times e to the negative j3t, when I multiply those, I add the exponents and I just get 0. So e to the 0 is 1. Okay, so this is just going to be 1/4 e to the j6t plus 2 plus e to the negative j6t. Okay, and now I'll expand this out again. So I get 1/4 e to the j6t plus a half plus 1/4 e to the negative j6t. Okay, and that is yet again the Fourier series. Okay, this is the Fourier series for cosine squared of 3t, but again, we want to make it look exactly like the Fourier series so we can specify the Fourier series coefficients as well. So we want to write this again as some constants times e to the j, an integer times omega naught times t, just as we've done so far. Okay, so I'm going to have a 4th times e to the j. Now, this is why we needed omega naught, right? Omega naught 6. So we want to write this as 1 times 6 times t plus 1/2. How do I write this as e to the j, some integer times omega naught times t? Well, just make that integer 0, right? Now this whole thing is just 1, which is what I want. And then plus 1/4 e to the j, negative 1 times 6 times t. And now we can read off what the Fourier series coefficients are. F sub 1 has to be a 4th. F sub 0 has to be a half. And f sub negative 1 has to be a 4th. Okay, and then f sub n is going to equal 0 otherwise. All right, so was that example just one little step up from before? Hopefully that's okay. Now let's do the next one. Okay, so the next example, we're going to look at a function that is cosine of 4t plus cosine of 6t. Okay, so what can we do here? Well, again, we know we want to find the fundamental frequency, and so one way to do that is to first find the period. So let's try and find the period of this function. So we can look at cosine of 4t. Looks like this. We know the period of that is 2 pi divided by 4, which is pi over 2. And we can also look at cosine of 6t. Something like that. Period of that is 2 pi divided by 6, or pi over 3. Okay, and as we saw in a previous video, since both of these functions equal 1 when t is 0, we really just want the first value of t that makes both of these functions equal 1 again. And we can see that this function equals 1 at pi over 3, this one at pi over 2. Clearly not at the same time, but if I repeat this function one more time, go all the way out to pi, and repeat this function 2 more times, all the way out to pi, and we can see that pi is the first t value where both of these functions equal 1 again. And that means that these functions will keep repeating after every interval of length pi. Okay, we can see from this that the period of f of t, this is just what we did in the periodicity video. The period of f of t is pi. And so omega naught is 2 pi divided by that period pi, which is 2. Okay, so omega naught is 2 here. But I'm going to follow the same procedure. I'm going to write these as using the same formula we were using earlier for cosine that we got from the complex numbers video. Okay, this is 1/2 e to the j4t plus 1/2 e to the negative j4t plus same thing for cosine of 6t. 1/2 e to the j60 plus 1/2 e to the negative j60. Okay. All right. And now let's again try and write this exactly. This is the Fourier series, but let's write it exactly so we can read off the Fourier series coefficients. Okay, we see omega naught is 2 here. Okay, so I'm going to write this as 1/2 e to the j 2 times t plus 1/2 e to the j negative 2 times t plus 1/2 e to the j 3 times t plus 1/2 e to the j negative 3 times t. And so you can see I've written all these exponential terms as some integer times the fundamental frequency too. Okay. So now I can just read off all the Fourier series coefficients. All the non-zero coefficients here are equal to 1/2, so I'll just write it like this. F sub 2 is the same as f sub negative 2, is the same as f sub 3, is the same as f sub negative 3. They're all equal to 1/2. Right? And f sub n equals 0 otherwise. Okay. So those were a bunch of examples where we didn't need to integrate. We could just kind of massage our original expression and be able to write it in terms of, or write it as the Fourier series. But now let's move on to another example, one more example, where we're actually going to use the formula we derived in the previous video. So now recall a formula to obtain f sub m. Okay, so we saw that that was integrating over, taking 1 over the period, and then we're going to integrate over an interval that has length the period. Our function e to the negative j and omega naught t dt. Okay, so now we're going to use that formula to get the Fourier series coefficients of a more complicated function. And that function is going to be the absolute value of sine of t. Okay, so what does that look like? Something like this. Absolute value of sine of t. T. Repeats. Okay, and how often does it repeat? Well, we know that sine looks like this, right? And so sine we know is 2 pi periodic. But we can see here that absolute value of sine of t actually repeats more frequently, repeats every pi. Okay, so the period of absolute value of sine of t is pi. Fundamental frequency is 2 pi divided by pi, which is 2. Okay, and now let's use that formula for the nth Fourier series coefficient to get what the Fourier series coefficient should be. Okay, now we can't just use something like we've been using previously, because if we tried to plug in for sine using that equation, e to the jt minus e to the negative jt over 2j, this absolute value sign around it would cause us problems. There's really not much we can do after that. Okay, so we have to use a different method. So we have 1 over the period here. The period we see is pi. So we're going to get 1 over pi. And now I have to integrate over an interval that has length pi. Now, which one should I choose? Well, technically you could choose any, but I think choosing from 0 to pi looks particularly nice. And why does that look so nice? Well, it's nice because when t is between 0 and pi, absolute value of sine of t actually just equals sine of t. Right? Sine of t looks like this. Absolute value of sine of t just flips that second part positive. But you can see between 0 and pi, they're the exact same function. Okay, so we're going to use that right now. Okay, we're going to use that. So let me just write it down first. E to the negative j, and omega naught's 2 here. So I'll write 2nt dt. Okay. All right, and now let's use what I just said. So when t is between 0 and pi, we're integrating between 0 and pi. Absolute value of sine of t actually just equals sine of t. They're the exact same function on that interval that we're integrating over. So this is because absolute value of sine of t equals sine of t when t is between 0 and pi. Okay. And that's really useful because now we have a much easier time integrating using sine of t than absolute value of sine of t, because now we don't have the absolute value bars. And so we can plug in, well, we can just do this integral. And I think the easiest way is to plug in for sine of t using our favorite expression. So it's 1 over 2j e to the jt minus e to the negative jt, e to the negative j 2nt dt. Okay, now we got to do this integral, and it does take some time, but we will get through it, and then we'll get a good answer at the end. Okay, so how can we do this? Well, let's try and split up this integral. First of all, I'll bring the 1 over 2j outside. So 1 over 2 by j. Okay, and now I'm going to have the integral from 0 to pi of e to the jt times e to the negative j2nt. Well, what is that really? That's just e to the j. And then I have a 1 minus 2n, and then a t. Okay, just combining those exponents. Integral from 0 to pi, or sorry, minus the integral from 0 to pi of this times that. So now I'm going to have an e to the negative j, and then a 1 plus 2n. Okay, just combining those exponents. Okay, now let's integrate. So what do we get? Well, we're going to get e to the j 1 minus 2nt. But with the chain rule, we need to divide by the thing multiplying the t in the exponent, which is j times 1 minus 2n. Okay, and normally we do have to be concerned that we're not dividing by 0 here. How can we be sure that this number here is never 0? Well, remember, n has to be an integer. Okay, so 1 minus 2 times an integer, that's never 0 because it's always an odd number. 1 minus an even number, 2 times some integer is always an odd number. Okay, so you can, plug in. When n is 0, we get 1 minus 2, it's negative 1, that's odd. When n is 1, we get 1 minus, or sorry, when n is 0, we just get 1. When n is 1, we get 1 minus 2, negative 1, that's odd. Right, we always get an odd number. It's just 1 minus an even number, so that has to be an odd number. So it can never be 0 because 0 is even. Okay, the other way to see it is to say, all right, what would n have to be to make that denominator 0? Okay, well, it would have to be a half, right? If n were a half, then 1 minus 2 times a half is 0. Okay, but n can't be a half, it has to be an integer. So we're never dividing by 0, so that's good. Now over here, what are we going to get? Sorry, we're going to get a negative from right there, and then e to the negative j 1 plus 2nt divided by negative j 1 plus 2n. Again, this number is always odd, we're never dividing by 0. And now I have these two negatives here, so I'll just get rid of this one, make that positive. All right. Oh, oops. And now I got to evaluate this from 0 to pi. Okay. So let's do that now. Okay, it's all going to simplify nicely, don't worry. Okay, so where are all the t's I have to plug into, right? Integrated dt, well, they're just right there and right there. Okay, so let's do that. So e to the j 1 minus 2n pi minus what I plug in when I plug in 0. Well, then I just get e to the 0, which is just 1. Divided by j 1 minus 2n. Plus, same thing here, e to the negative j 1 plus 2n pi. And then minus what I get when I plug in 0, which again, e to the 0 is 1. Or j 1 plus 2n. Okay, so far so good. Now I want a way to simplify these expressions. And it turns out we can, because kind of what I was saying before, let me just make a note. 1 minus 2n and 1 plus 2n are odd numbers for any integer n. Okay, so what does that mean? For e to the j 1 minus 2n pi. Well, if that's always an odd number, think about what's happening in the complex plane. Like if it was 1, I'd do e to the j 1 times pi, which gives me the value -1. What if it were 3? I'd go 1, 2, 3, right? E to the j 3 pi, and I get back to -1. I could go around the circle once more to get to e to the j 5 pi, also back at -1. In other words, e to the j, some odd number times pi, is always -1. Okay, it's always -1. And there are many ways to see that. You can expand this with Euler's formula, right? There's many ways to see that this is always -1, but it is, as long as that number there is pi, or sorry, is odd. So this is always -1, and then same thing for this term, right? You know, negative j 1 plus 2n pi, because again, you know, whenever I go, whenever my angle of a complex number on the unit circle is an odd multiple of pi, I'm always going to end up over here, right at -1. Okay. All right. So that's true, and that's for any integer n. And we know that n for us is always an integer, right, in that Fourier series. And so we know that these terms right there are always going to equal -1 for any n. So we can just plug in for that. So -1 here, -1, give me -2. Plus -1 minus 1, again, is -2 over j 1 plus 2n. Okay. I'll just make a note if you're looking at this later and just think about the complex plane. Or you can expand with Euler's and use properties of sine and cosine, whatever you like. Okay, now what can I do? Well, how about I bring this j outside? Okay, when I bring the j outside from both those terms, I already have a j, so I'll get a -1. So in total, I'll have a -1 times this 2. And then when I bring out this -2 from both of these terms, it'll cancel that. So in the end, I'll just end up with 1 over pi times 1 over 1 minus 2m plus 1 over 1 plus 2m. Okay, now I just want to put these two terms over a common denominator. Okay, so that common denominator is going to be the product of those denominators. So let's just check what that is. 1 minus 2n times 1 plus 2n is going to be 1. And then I'm going to get plus 2n minus 2n, those cancel, and then minus 4n squared. Okay, so I'm going to get 1 over pi. Multiply this top and bottom by 1 plus 2n, gives me 1 plus 2n. Okay, it's all going to be divided by that common denominator, 1 minus 4n squared. And then I have to add, you know, what I get when I multiply top and bottom of this term by 1 minus 2n. So I'll just plus 1 minus 2n. And I already have the denominator. You can see the two n's in the numerator cancel. And I just end up with a nice simple expression, 2 over pi times 1 over 1 minus 4n squared. Okay, and that's it. So those are our Fourier series coefficients for absolute value of sine of t. Okay, so let's just sum it up here. Absolute value of sine of t, okay, it has this Fourier series representation. And we actually found what those Fourier series coefficients are. So I'll just plug in for these right now. So the 2 over pi doesn't depend on n, so I can write it outside. And I have the sum. And then I just have these terms divided by this. So remember, what was our omega naught? I think it was 2. Yeah, omega naught was 2. Okay, so I'm going to get e to the j, I'll write it as 2jnt divided by 1 minus 4n squared. from our Fourier series coefficients. So there you go. So that is our representation. Well, not a representation, it equals. Sine, absolute value of sine of t actually equals this big summation. Pretty cool. So yeah, so that is this example. And that's all I had for this video. I will see you in the next one.